Okay, good morning, one and all. So this is our third class of this week. So we have completed our topics regarding our heating. So these are this syllabus we are dealing with the second units. Up to now, we have completed this advantages and methods of electric heating. In this methods of electric heating, just we have seen resistance heating and arc heating. So these heatings are going to be covered under your classification, that is power frequency. So there is another two methods. We are going to deal with high frequency heating, that is induction heating and dielectric heating. So up to yesterday class, we have seen arc heatings. So based upon that, we are going to have some problems. So all this we have covered in the last classes. So one thing, yesterday in the group, I have posted the total first unit of your drives. So please check the group and download the document and prepare for the exams. Okay. So all these things we have covered: resistance heating, direct resistance heating, indirect resistance heating, and some of the examples which covers under your resistance heating. Okay. So let's have our problems today. Yes, this is the arc heating. Yesterday we have completed this topic. So we are going, this arc heating has been classified into two types. That is direct arc heating and indirect arc heating. That is, we have shown with diagrams. So, okay, up to this, yesterday we have covered. Now, please, everyone note this problem. Please check the problem, what he has asked and what we have to find out. So calculate the time taken to melt 5 ton of steel in 3-phase arc furnace having the following data. So he has given the data clearly. So like these problems, you are very easy to get that minimum 2 marks by writing the given data from the given problem. Okay. Check out what are the terms they has given. So he has given the following data as current, it has 8000 amperes, resistance 0.003 ohms, arc voltage. So that is the voltage which was produced by the arc between the electrodes, that is 50 volts. The reactance is 0.005 ohms, latent heat 8.89 kilocalories per kg. So he has mentioned here per kg, but the material which we have taken is 5 tons. Okay. So the specific heat of that material is 0.12 and the initial temperature of the material is 18 degrees. After the production of your heat, that is through the arc, the melting point at the temperature at which the material going to melt, that melting point is 1370 degrees centigrade. So the overall efficiency by this process we are going to get is 50%. So from this data, he is asking to find out the power factor, that is cos phi, and the electrical efficiency of the furnace. Okay, please note down this data. Please note down this data from the question. So it is easy and simple problem. You can get directly 7 marks. So sometimes they are going to ask to solve this problem for 14 marks also. So earlier I said just by writing the data which he has asked in the problem, Thereby you are going to get the 2 marks easily. So by putting the formulas, you are going to get another 2 marks. If there are any diagrams or equivalent circuits, there you are going to get 2 marks. There only you are going to score half of the marks, about 14 marks. Okay, so let us step into our solution. So first of all, we will see the equivalent circuit, how it is going to be drawn. The equivalent circuit of your furnace. This is the equivalent circuit of your arc furnace. So here one thing I would like to ask you. Okay. So while seeing this one, can you identify which type of arc furnace we are using here? Either it is a direct arc furnace or indirect arc furnace. So I enable the chat box. You can have your answers in that chat box. Okay. From this equivalent circuit, by this term, can you identify? Yes, this is an indirect arc furnace. We are not going to place any electrodes and producing the arc to the charge directly. So just we are placing this is in a horizontal. So in this diagram we have shown is vertical, but when coming to this is an indirect. So this is the equivalent circuit. So here all we know the power V is equal to IR. The input power P is nothing but VI. Sorry, P is equal to VI. Let me see. Yes, okay. So all the power is nothing but we all know voltage into current. But from the voltage, current and resistance equations, we all know that V is equal to IR. So this power is the input power. We have considered this as an input power. So we will calculate that input power. So before that, we are going to have the supply voltage. This EA is the arc voltage at the load side. The electrodes which was connected at these two terminals at this is considered to be in a load. So the voltage which was produced by this arc is equals to, he has given, that's 50 volts is given. It is in a 50 volts. EA is nothing but your 50 volts. The resistance R and the reactance, both those values are 0.003. So in the exam, in the main exam also, you have to represent like this. So then only it is very clear and you will get the good marks, 0.005. It is not difficult. Just by drawing this equivalent circuit, from the given data, you can easily place the values of the elements which what we have placed in this circuit. Okay, this is a transformer for by using tap changing, we are going to control the voltage of your circuit. Okay, so let us calculate this arc resistance. So now we have to calculate the arc resistance per phase, but here he has given the three phase supply, to the arc furnace to melt the 5 ton of the steel. So now, but one thing we have to remember in this last class, whatever this indirect arc furnace we are using here, we cannot going to use any 3-phase supply. That's why we are going to calculate all the terms in the per phase. And finally, we are going to multiply with the 3. Then only you are going to get 3 into single phases gives your 3 phases. That's why we are going to calculate each and every element per phase values. Okay, please remember that. So in this indirect furnace, we are not going to place any third electrode to produce the arc. So here there is only two electrodes sufficient to produce your arc. So let us calculate the arc resistance per phase. So here I have given the value directly. There is nothing but, let me scroll down. See, R is nothing but we from the above formula. Above formula V is equal to IR, where R is equal to V by I. So this is V is nothing but your arc voltage. So whatever the voltage here produced, this is also a 50 voltage in parallel connections. The voltage produced at the terminals are going to be equal. So V is nothing but your arc voltage, and current here he has given I value 8000 amperes. So same here I have written, that is V by I, 50 by 8000, we got 0.00625. Please check the value. Have you got it or not? Now, from this equivalent circuit, we have to calculate the voltage drops. Voltage drops across this resistance and across this reactance. Okay, that is nothing but what is the formula or the value we can have across here. That is nothing but whatever the voltage drop. Voltage drop means all all well know, that is V is equal to IR. That is the voltage drop. So the I which was passing through this element. So the product of this current and the resistance value. Thus I into RT gives your voltage drop across your resistance. The same thing, the current passes through this reactance. So I into XT gives your voltage drop across your reactance. Okay, the same things we have to calculate here. See, the drop due to the resistance of the transformer, that is I into RT, R suffix T. So I, all you know, that has given in the data, that is 8 amperes, 8000 amperes into the resistance of your transformer, that is nothing but 0.003. So the total value is 24 volts. And the drop due to the reactance of the transformer, that is I into XT. Now you have to calculate, the next step is I into XT. That is 8000 into 0.005. Okay, 0.005. So see, let us see how much the values. That is 40 volts. That is 40 volts. So from this diagram, the voltage across this arc has been produced as 50 volts, but the voltage drop across this resistance by the calculations we got, this is in a 24 volts, and the voltage drop across this reactance is 40 volts. Okay, is it clear? The voltage drop across, we have calculated the voltage drop across the resistance and reactance of your transformer. Why? Because these are the elements which was connected to the secondary terminals of your transformers. That is 24 volts and 40 volts by the calculations. Okay, next what we have to do, just from this equivalent circuit diagram, just let us consider the some phasor diagram. Okay, yeah, see, this is your phasor diagram. So the resistance, the voltage drop across the resistance and the voltage which was applied across the arc, the voltage developed across the arc between the two electrodes is EA. So both the drops are going to be in phase, are in phase. Okay, so this XT, that is nothing but the voltage drop across the reactance. So both are going to be in the 90 degrees. So the resultant voltage between this voltage drop of the resistance and the arc to the voltage drop across the reactance is the your resultant voltage, that is the supply voltage. Okay, So from this phasor diagram, so what we can do, what we are going to calculate, check out the resultant voltage. That is, all you know that in trigonometry, in right angle triangle, we can have this hypotenuse square is equal to side square plus side square. So here hypotenuse is your voltage, supply voltage. So that is nothing but arc voltage, sorry, not in a supply voltage. The V is nothing but the voltage which was produced at the secondary side, that is going to be equals to the is from the voltage here what we have considered here, this V. This is the arc voltage. So now we have to, just let me check it out. So the voltage, yes, okay. From this phasor diagram, let us calculate the resultant voltage. So I think it is not going to be the value of the arc voltage. This is then a resultant voltage between the voltage drawn between these two phasors. Sorry, don't compare this one with an arc voltage. This is different. From the phasor diagram, it has been taken as then a resultant voltage. So now we have to calculate the resultant voltage. So V square is equals to EA plus I into RT whole square plus I into XT whole square. So from this, V is equals to square root of EA plus I into RT whole square plus I into XT whole square. Okay. From the above steps, we have calculated the I into RT, that is 24 volts, I into XT 40 volts, EA is your 50 volts. So please, placing the values, tell me the answer, the resultant voltage from the phasor diagram, what you have got. The value of this resultant voltage, 84.11. Let us check with this. 84.118 volts. Okay. From the phasor diagram, we have calculated the resultant voltage of your equivalent circuit. So now the next step, the main thing is we have to calculate the heat requirement. How much the amount of heat is going to be required to melt the metal per kg. He has given the total weight, that is 5 tons. But in the problem, what he has asked, he has given the latent heat, that is for kg, not for the total weight. So that's why we have to calculate, first of all, the amount of heat required to melt per kg. So how you are going to have the, that is specific heat into final temperature minus initial temperature plus latent heat. So that is the thing we have to, the amount of heat required. So from this triangle also here, the cos phi. So he has asked the power factor. So we can calculate, that is cos phi is adjacent by hypotenuse. Hypotenuse nothing but your resultant velocity, resultant voltage that we have calculated. We got 84.118. Please check this value. From this phasor diagram, we can calculate the power factor, that is cos phi. So this is the adjacent side, this is opposite side. From trigonometry, this is hypotenuse. From the trigonometry, we can have the basic formula, cos phi, which is phi is nothing but an angle which was considered between the resultant voltage and the phasor. So cos phi is equal to adjacent by hypotenuse. Adjacent by hypotenuse. So what is the adjacent side? The sum of these two phases, that is EA plus IRT. That is the thing I have written here. By hypotenuse is equal to is resultant voltage. So that is V. So these two values you have calculated earlier. That is EA is equal to 50 has given in the data, and IRT, this is T suffix T. So you have calculated that is 24 volts. So by placing these values and this value, we are going to get the value of your power factor. That is 0.879 lagging factor. 8.79 lagging factor. So the first case has been calculated. So in the problem, he has asked to derive the power factor and thermal efficiency. So the first step we have covered here from the phasor diagram. So from the given data, we have calculated this power factor cos phi. Okay, fine. Here we have completed first step. So our final step we have to calculate is the thermal efficiency. For that, whatever the steps required, let us see. So first of all, we have to calculate amount of heat is going to be required per kg of steel to melt the given material. So for that, we are going to have the formula, that is specific heat into final temperature minus initial temperature, the difference between final temperature and initial temperature, plus the latent heat of the material. So specific heat, the specific heat of the steel as given 0.12 into the final temperature T2 minus T1. So initial temperature of the material, that is 18 degrees centigrade, and the operating temperature, that is the temperature at which the material is going to be melt, that is 1320 degrees centigrade. He has given in the data. We are not going to take any extra data from anywhere else. Just for whatever the data given, we have taken. Okay, 171.13 volts, right? Let us check the answer. Yes, 171.13 kilocalories. Kilocalories. Now, here what we have done, just we have calculated the amount of heat required to melt the steel per kg. So, this amount of heat, that is 171.13 kilocalories. This amount of heat is required only to melt the 1 kg of steel, but the total weight of the material has been given as 5 tons. So let us calculate amount of heat required to melt the 5 tons of steel. So here this, whatever we have calculated the amount of heat required per kg of steel, but here we have given 5 tons. So the total heat required for 5 ton, 5 into that is, let us move this window. Okay, here 5 ton. 5 ton means 5000. 1 ton is equal to 1000 kgs. So 5000 into whatever the amount required, we calculated, that is 171.18. That is, we are going to get the amount of heat we required, that is 855 650 kilocalories. Okay, have you got? So you can write it as 855.650 into 10 power 6 calories. So that much amount of heat we require to melt the 5000 5 ton of steel. Okay. Now we have to calculate the actual heat required. This actual required, because here we got the value in kilocalories. We got the values in kilocalories. now we are going to convert into kilowatt hour. Kilowatt hour. So for this, for 1 kilocalorie, the value is 1.160 into 10 power minus 3. One kilocalorie is equal to 1.162 into 10 power minus 3. Just let me go to the one's problem. What the solution? 0.5. 3 phase ones. 0.05. Yes. Okay. So how we have calculated this? There's nothing but here. I think everyone will got the doubt. I think how this has been taken as. So the actual heat required is going to be considered as the efficiency. The efficiency of your metal has given as 50%. That is 0.5. So the efficiency is equals to the heat required. Please note down this formula. Heat required for 5 ton, for 5 ton, that is total weight of ton, to actual heat required. Actual heat required. So from this you have calculated the heat required for 5 ton, that is 8,55,650 kilocalories. Okay, right? So efficiency he has given as 50%. That is 50 by 100, 0.5. So you know this value, you know this value. From this formula, you are going to calculate this actual heat required. That is the amount of heat required for 5 ton kgs per efficiency. That is 0.5. So there you are going to, I just drop the values directly in this formula. So that's why I'm going to give you the formula how we have taken this values, this ratio values. Okay. Please note down this formula here. From the efficiency is equal to heat required for 5 kg, heat required for 5 ton to the actual heat required. So we don't know the actual heat required. Okay, that's why we are going to calculate here itself. Okay, I think all you noted, so just I am erasing all these things. Okay, so now we have calculated the actual heat. Now from this we can have, from the data we have the first formula I have said, the input power, the power input. So it can be considered. So here now we are going to consider the power factor because we are going to use here AC supply. Okay, for the AC supply you are going to use we are going to include the power factor also. Therefore, power input can be considered as VI cos phi, VI cos phi into 10 power minus 3. So by placing these values, please have your answer in the chat box by solving this. Why? Because here we are going to place is we are considering the 3 phase. Here we are going to consider the 3 phase. So I'm going to show the value. Yes, right. I think only 253 is solving the problem. And what about rest of others? What about the rest? Please practice the sums because from the problems you can score easily full marks. So here 3 VI cos 5 into 10 power minus 3. So V is your resultant voltage. So we have calculated 84.118 into I has given 8000 amperes, and cos phi we have calculated earlier, that is our first part, that is 0.879 lagging power factor into 10 power minus 3. So we go this value. This is your power input. So here, as earlier I have said, everything is going to depends upon your time period. So now we have to calculate the time requirement. How much the time? So he has given, right? He has given the total weight of the material, and he has asked to calculate the thermal efficiency. So by heating, by producing this arc heating, or by employing this indirect arc heating method, so we have calculated how much amount of heat is required to melt the total amount of material, that is 5 ton. But here also we have to consider, to calculate the efficiency, how much of time is required to produce this much of amount of heat to melt the 5 ton of the steel. Okay, so now we have to calculate the time requirement. So here is this, whatever the actual heat we require to heating purpose to the power input. So the ratio of these two terms gives your time requirement. So please calculate this. 1988.53 kilowatt hour by 1774.55 kilowatts. Please use your calculators. So it's already 40 minutes for one problem we took it. 1.12. So what is this? 1.12 is in minutes or hours? Yes, per hour. So now we convert this hour into minutes. So how many minutes you will get? Let us see. 67.2. So we can easily say that's 1 hour is nothing but 60 minutes. So by calculating this, by converting this hours into minutes, the final time required. So 67.2 minutes or 1 hour 12 minutes we required to what we want to do, to melt the given material at the heat of 1988.53 kilowatt hour. So finally we are going to calculate the thermal efficiency. So anyone can have this efficiency? All you know, the efficiency is nothing but output power by input power. Output power by input power. So calculate this thermal efficiency of the furnace. That is 3 VI by input power. Input power is 1774.55 kilowatts. So I have converted into watts, that is into 10 power 3 watts. So this is input power. Output power is 3 into VI. V is the voltage, arc voltage, because that is the output voltage. So the current is nothing but 8000 amperes. So all you have calculated the values. So just place the values here. You can have this, that is nothing but output by input. That is nothing but VI. This is for single phase, but they has given the three phase supply for the arc furnace to melt the material. That's why 3 Vi into input power, that is Vi cos phi. We have already power input. We have calculated the value, that is 1774.55. So for percentage, we are multiplying with the 100. That's it. Don't be confused how this 100 has been taken. So the efficiency we are going to measure in percentage. So that's why I have calculated with 100. So that is the thermal efficiency. So from this problem, you can easily understand. So how much of time is required to melt the given amount of material or your charge, to heat the charge. Charge is nothing but here the steel. So he has given the latent heat per kg. So we shouldn't consider that latent heat completely to the fighter. So there is the one important thing you have to note there. So and we have to calculate the heat required for kg and also heat required for total amount just by multiplying the amount of heat required for the per kg into the total amount he has given. So actual heat also we have to be required. So from both these things we are going to calculate the power input. So here also one important point we have to be note is the time requirement. How much the time? Because that is also one thing, important factor we have to consider. Because according to the time of supply, that is on and off, we have earlier seen in the previous slides, that is in the previous classes, some of the essential factors we have to consider while these heating methods or temperature control, because here the on and off times of your supply is also very important point. That's why we have calculated here how much of time is going to be required for your heating process. So from this we have got the 67.2. So from all the above steps we have calculated this thermal efficiency. So for melting up of 5 tons of your steel, after melting up, the efficiency of the furnace is going to be 67.62 percentage. Okay. So I'm going to step into next problem. So this is also an easy and simple thing, same as earlier. So here, please check out the problem. So I'm going to discuss only these two problems because these two questions has been asked in all the textbooks also. Yeah, in any textbook, if you refer whatever the problem we have solved before this problem has been given in each and every textbook with the change of values. That's it. The problem is same, but from variation of from one textbook to other textbook, they have changed the values. That's it. But the question is same. You can refer to any book. Is the Rajput or uh, some of the books we have here. Mehta, all these things. What Mehta? Let me check. You can refer Ramlingam, M. Ramlingam, that is electrical utilization and fraction. And also you, for the problems, you can refer to the Rajput and also C.L. Wadhwa, J.B. Gupta. So these four books are very good at problems, because in these four books, the same problems has been given just by changing the values. Just by changing the values. Okay. Let us see. Let us complete this problem and we will end up with this class for today's class. Okay, let us see. A 100 kilowatts Ajax watt furnace works at a secondary voltage of 12 volts at power factor 0.6 when fully charged. If the reactance just it's not moving here, the charge remains constant but the resistance is, if the reactance presented by the charge remains constant, but the resistance varies inward as the charge depth in the furnace. Calculate the charge depth and that produces maximum heating effect when the furnace is fully charged. So he is asking to calculate the depth of your charge, that is which the material which we wants to be heated. So how much in that furnace named as Ajax vat. The furnace name is Ajax vat. In that furnace, he has kept the charge, but he wants to calculate the depth of the charge where that produces maximum heating effect. When the furnace gets fully charged, thus we have charged fully the furnace. So how much of maximum heating effect is going to be produced? So at that maximum heating effect, how much of the depth we have taken to heat up the charge? So that is the problem he has asked. For that, he has given the data. He has connected the secondary voltage, that is the transformer. The secondary voltage is 12 volts at a power factor. He has given the power factor directly itself. We are not going to calculate any power factor cos phi. Okay, 0.6. Okay, let us see steps of this problem. So here he has given the secondary voltage, okay, and the power factor. So from this P is equal to V2 I2 cos phi. So we know the power because the value of this furnace is 100 kilowatts. He has given. The V2 is the secondary voltage, 12 volts. P is equal to 100 kilowatts. V2. Why we are going to V2 means he has specifically mentioned that secondary side. So primary side is going to be considered as V1 and secondary side we are going to mention as V2. So the voltage of V2 is 12 volts. And the power factor cos phi is equal to 0.6. So the last term is I2. We don't know. So whatever the current is going to be produced at the secondary side, we have to calculate. I2 is equal to P by V2 into cos phi. Please place the values in above equations. In this equation, please and calculate the current at the secondary side. P is 100 kilowatts, that is 100 into 10 power 3 by V2 is 12 volts, 12 into cos phi is 0.6. So please have your answers in the chat box. 13.88 into 10 power 3 amperes. Okay, that's where let us check. 100 into 10 power 3 into 13 point. So here just I have considered as the, okay, fine. We can take it as kilo amperes. Just I have written here as a kilo amperes, or 13.88 into 10 power, we can take it as 13.88 into 10 power 3 amps or kilo amps. Okay, let us. He has given us when the crucible is fully charged, that is nothing but your furnace. Crucible is nothing but fully charged. Then the secondary impedance. So here he is going to calculate the impedance value. Z value. So what is the formula of the secondary side? Z2 is equal to V2 by R2. I2. Sorry, V2 by I2. Okay. So you have calculated from the problem. He has given the value V2. Okay, that is 12. I2 we have calculated 13.88 kilo amperes. So from this, you by placing these values, you can calculate your secondary impedance. 12 by 13.88 into 10 power 3. So please check the solution. She's got 0.86. Okay, fine. 0.0086 ohms, because impedance here, this impedance, resistance and impedance, we are going to have this ohms. Just for thing, instead of 0.0008, I have taken as 0.0864 milliohms. Milli is nothing but 0.864 into 10 power minus 3 ohms, 0.864. Okay, this is your secondary impedance when the furnace has been fully charged. From the impedance triangle, so I think all you well aware of that impedance triangle. So this is Z, okay, this is X, this is R, this is your angle. So the reactance of the circuit and the resistance of the circuit, so this is the resultant. There is nothing but impedance. Okay, so here we have considered this phase angle mirrors. So from this we can calculate this cos phi, cos phi, because here we considered, he has given, so especially he has given the secondary side, that's why we are making the terminals as R2, X2 and Z2. So from this we have calculated, we are going to calculate the cos phi 2. So secondary phase angle, that is cos phi 2 or cos phi, we can take it as. So that is R2 by Z2. So from this we don't have any value regarding the resistance value, just we have calculated only the reactance, and we have, sorry, we have calculated the impedance value Z2 in the earlier step. We have calculated the Z2. We from this question, we are not going to have any values regarding this resistance and reactance of the transformers. Okay, just we are going to calculate from this impedance triangle. From this equation, I am going to take R2 is equal to Z2 into cos phi. So here the Z2 value we have calculated 0.862 into 10 power milliohms. Sorry, milliohms, that is the value. Yes, milliohms, 0.864 milliohms into cos phi he has given, that is 0.6. So just placing the values here for this clumsiness, I think I'm going to erase all the insets. Okay. So by placing this, you're going to get 0.5184 milliohms. Yes, 0.5184 milliohms. From this impedance triangle, so we can calculate the secondary reactance. That is nothing but, all you know, here let me have this triangle Z X, sorry, Z2, X2 and R2. Okay, Z2, R2 and X2. So from the same formula, hypotenuse square is equal to side square plus side square. So in the previous step, you have calculated the R2 and Z2 values. So we know the two values. There is no any difficult to finding the third value. From this, hypotenuse square is equal to side square plus side square, where we all know this two. So 0.6912 milliohms, right? Okay, let us check this value or not. So that's placing 0.69 millivolts. Milliohms. Milliohms. This is the typing mistake. Milliohms. Okay. So you have calculated. Now we have the values Z2, R2, and X2. Okay. Now what we are going to do? He has given C. From the diagram, not the diagram, from the problem itself I have taken. So I have considered the capital H be the height of the, so because he has asked the depth of the charge, how much of the depth we have considered to keep the charge to be heated. So for that, I have just make it as this capital H be the height of the crucible. That is nothing but your furnace. The furnace height has been taken as capital H, and the height of the charge, that is HM. H suffix M. I have taken this HM as a height of your charge. So where we can get the maximum heating effect. Okay. So the small h is nothing but the heating effect. Heating effect. Heating effect. That implies h is equals to how much the height of the charge to the total height of the crucibles things. Okay. So here some of the specifications we have considered here. Let Rm be the maximum resistance of the maximum heating. At the maximum possible heating effect, the resistance of your charge has been considered as Rm. The at it's not moving this window. Okay, fine. At equilibrium point, we are taking this the maximum resistance, which is equals to the reactance of your secondary side. So at this point, the heat produced will be the maximum. So the maximum amount of heat can be produced at this point when at the equilibrium point. That is nothing but at the maximum resistance, which is equals to the value of your secondary reactance. Okay. So from this, by using this above equation, now I'm going to have the equation number 1. So by solving this, I'm going to have this equation. Please check it out. Finally, you have calculated this HM. HM is nothing but your height of your charge or the depth of the charge, that is 0.75 times the height of your furnace. That is in the above equation, H is equal to HM by H, that is R2 by Rm. So where here clearly I have mentioned which the height of the material is inversely proportional to the resistance of the material. This is here I have written this height of the charge HM. So there is no any interconnection between the resistance and the height where you kept the charge for the heating. So that's why this relation holds. The height of the is going to be your is inversely proportional. So from this conditions or the relationships, we have this equation, that is HM by H. If you taken this ratio, that is R2 by Rm. If you consider H by HM, that is Rm by R2. It is going to be inversely proportional and it is going to be the 1 by H. If you change these values, this heating is also going to be in a change 1 by H. So from this, you have changed at the Rm, where the value of x2 we have considered. So we have replaced it with this Rm as at the equilibrium position. At the thermal equilibrium, we are going to take this charge resistance is equals to the reactance of your secondary side. So we are just replacing by having the values. H is equal to R2 is nothing but we have calculated, and X2 also we calculated secondary side reactance and the resistance. From this you got the H value. So just placing the value H in this above equation, in the first equation, H is equal to HM by H. That is, we required the depth of your charge to be heated where the maximum amount of heat is possible. Okay. So this is. So this is the simple problem. This has been asked for 7 marks. So at this point, I am going to wind up this class. Okay. So these are the types of the problems you are going to face in the examinations, either in the mid or in the final examinations. So please practice at your home, because these are the simple things you can easily score full marks. Okay. when coming to the theory part, as of much you written, you are not going to score full marks. You can get the maximum marks, okay, but the full scoring marks is going to be done in this section only. That is the problems and diagrammatics. Okay, fine. I'm going to conclude this class for today's. So if you have any queries, please have your questions in our WhatsApp group. So I will get back to you. So once again, I am saying that please go through the PDF document which I have posted yesterday night. So that is the complete full contents of your first chapter, which we have completed in earlier classes. Okay. So regarding any doubts of your first chapter and up to this class, please have your questions in the chat box or in the concerned WhatsApp group. Okay. Thank you all. Have a nice day and be safe at your home. Thank you.